Okay, in today's lesson, we are going to transform logarithmic equations. Now, logarithms are the inverse of exponential functions. So I put the exponential function part of our pink notes down here at the bottom so we can reference this a little bit. Now, there are going to be some differences here today, and I'll explain those as we go, but basically they are inverses of one another. Now, when we look at this equation of log of x, there are some things that are unwritten but understood. So when we look at this, this is a log with a base of 10 of x. Now, we use that base of 10 so much that we don't even write it, and we just refer to it as the common log. And if anything besides 10 is used, then we have to write it. But if it's a 10, we don't have to. That's why it looks like this here. And it's this reason, the base is 10, that it's not exactly the inverse of this exponential on our pink notes, because the pink notes has a base of 2. So it's slightly different, but there are some similarities in what's going to happen. So for one thing, like our asymptote here was the x-axis, right? Well, if we flip that, our asymptote for the logarithmic function is just the y-axis. Okay? So that would be x equals 0, because that's the asymptote, right? Now, there are some points that we want to visit on this, and there's really only two that you need to worry about, okay? And so I'll give you these. So so here are the points that we use to graph our exponentials. So there is one point that switches x and y for the inverse, truly. So that would switch from 1 to 0. 1, 0 instead of 0, 1. It becomes 1, 0. Now, so that goes right there. Now, the next point, and the only other point you really need, is this one, and it's 10, 1. And how did I get that? Well, I got that because the base is 10. That means it takes 10 units horizontally to get up 1 unit. So my next point, this is a 10 by 10 grid, so it's just going to come over here, and it's going to make a lazy looking L. All right, it looks like this. So you can kind of visually see that this one has an L this way, but it kind of flips this way, and that's not very curved, but you get the idea. So, but really there's 2 points you need, the 1, 0, and that will be true of any base equation, any base logarithm, and then the 10, 1, and that's for base 10. Now in reality, if you have a different base, this point just becomes whatever that base is, 1, okay? So you can adapt that as necessary. Now let's go back and do domain and range for the logarithm. All right, so look at our x values. Look, they approach 0, but they never actually touch 0. And then they go on to the right forever, so it goes to infinity. So in our two notations, we're going to say x such that x is greater than 0. Notice I don't have the or equal sign because it can't equal 0, but it approaches it. So in interval notation, that would be a parenthesis 0 to positive infinity. Now range, it's from bottom to top, it's going to negative infinity, and it is going to positive infinity. It's just growing very, very, very slowly. So this one is y such that y is an element of all real numbers. And in interval, it's negative infinity to positive infinity. Now x-intercept, it does have an x-intercept at 1, 0, but it does not have a y-intercept because it never touches that y-axis because of the asymptote. Now, if you step back and look, remember how we talked about domain and range are opposites for inverses? Look, my domain for my exponential is the range for the logarithmic, and the range for the exponential is the domain for the logarithmic. So this part is true. My x-intercept, or I'm sorry, my y-intercept for exponential became the x-intercept for the logarithmic. The asymptote switched as well. So there are some similarities in the pattern of inverses, but like I said, we're going to use a base 10 here, so it's going to be slightly different than the base 2 that we're going to use for exponential. Let's move on to the next page of your assignment. Now, right, looking at our equation, this is a very generic form of the logarithmic equation. A is something we're familiar with. That's going to be our vertical stretch and shrink. C is affecting the left and right because it's in parentheses with the x, and the D is the vertical shifting up and down. Now this B value is kind of new, but it's just the base. It's just the base. So the B value does not affect the transformations at all. Okay, it won't affect it. It's just the base. It tells you how slow it grows. The B value is how long it takes for the Y value to get to 1. Remember, it's base 1. That's your second point. It tells you how long it takes that Y value to get to 1. The C value is telling us which way it moves left and right, but honestly, with our asymptote, our vertical asymptote, the C value tells us where the vertical asymptote will be. So it'll be x equals whatever C is. All right, and we'll model this for you as we go along. Now let's look at this first part of our assignment. List the transformations to each logarithmic function, giving the direction and the amount of movement. So we're just describing here. Okay, we're just describing. So let's look at this. Log base 2 of x minus 4 plus 20. Well, the base 2 doesn't really matter, so don't describe the 2. But remember, what's happening to x is always the opposite of logic. So that minus 4 means it's going right 4. The plus 20 means it's going up 20, and that's your answer. Number 2, that 1/4 is out front, so that is a vertical shrink by 1/4. Okay, remember, if it's a fraction, it's a shrink. Number 3, log base 4 doesn't matter. Okay, that's just the base. And there's x. Nothing really is happening to x, but this plus 20 is on the back side, so that means all it's doing is moving up 20 units. All right, look at number 4. We have a negative, and we have a 3, and the x is being moved plus 9. So let's do this. The negative is a vertical reflection. The 3 is a vertical stretch. And then the plus 9 means it's moving left 9 units. Okay, my asymptote's moving left. All right, so as we look at these, let's look at our graphs, and let's kind of go through and list our transformations, and then we'll come back and graph them, okay? On number 5, look what's happening. That plus 2 is moving it up 2. Number 6, the x minus 2 means it's moving right 2. The plus 1 is moving it up 1. 7, that 2 is a vertical stretch by 2. The minus 5 is moving it down 5. Number 8, the negative is a vertical reflection. The plus 5 is in parentheses, so it's opposite logic. It's moving left 5 units. Number 9, that 1/2 is a vertical shrink by 1/2, and the plus 4 means it's moving left 4. Number 10, don't let the log base 6 mess with you. That's just the parent function. So what we're focused on is this minus 2, and that just means it's moving down 2 units. All right, now let's go back to number 5 and graph this, okay? Now you're going to want to have a straight edge because you got to put in asymptotes on all these graphs. So let's look at this. Remember we said this one is just moving up 2. So we're going to, our origin that was at 0, 0, we're just moving it up 2 units, so put a little plus sign. That is your new origin. And then you're going to draw in your vertical asymptote through that origin, that new origin that you've created. Now, if you recall, those parent points that we've discussed are here. Remember, it goes 1, 0 from the origin and then 10, 1 from the origin, and we already have our asymptote. We already established that. Now, so from my new origin, I'm going to go right 1 and at 0, and then I'm going to go right 10 from that origin, so that puts me all the way over here with that point up here. And then you want to move or draw your line through it. I want to make it like a curvy L, not a straight 90-degree angle. Make it curved like that. And that's all there is to that graph. Let's look at number 6. This one is moving right 2 and up 1. So my new origin is here. So I'm going to put my vertical asymptote right in through that origin. And I'm going to do the same thing. Using my parent points, it says go right 1, but up none. So right 1, up none. And then it says go right 10, up 1. So I'm going to have to scooch over here because I don't have enough graph here. But let's see, 1, 2, 9, 10. So this is where it's going to go. Okay, so my graph wasn't quite long enough, but you can adapt. You can do this. Look at number 7. This one has a vertical stretch by 2 and down 5. So my origin is just moving down 5. The vertical asymptote goes through that origin. So draw that in nice and thick, but dotted. It has to be dotted. And now the vertical stretch. Remember, the vertical stretch takes the y values and multiplies it by whatever number. But look at our point. Our first point is 1, 0. So if I multiply the 0 by 2, it's still 0. So the nice thing about logarithms is it's always going to go through this point. No matter what the vertical stretch or shrink is, it's really it's not changing because 0 times anything is still 0. So if I start from my new origin, I still go over right 1, up 0. And then I'm going to go right 10 and up. And this time it's not 1, it's 1 times that 2. So I'm going to go right 10, up 2. All right, so that's where you see the stretch on that second point, not on that first point. Let's go to number 8. Vertical reflecting, but left 5. So let's go left 5 first. All right. And draw on my vertical asymptote. Now if I go to my points, look what I'm going to do. I'm vertical reflecting, so that means I'm taking my y values and multiplying by -1. So again, if you just go right 1, that 0 doesn't change. It's going to stay right where it was. However, when I go over 10, instead of going up 1, I'm going to go down 1. So let's look at this. Let's count 10 from here. 6, 7, 8, 9, 10. So I'm going to go down 1. Instead of staying there, I'm going to go down. All right, now it's reflecting, so it's going to go the opposite direction. Oops. Okay, so it's going to be the upside down. Remember, it reflected, so it's going the opposite direction. Let's look at number 9. A vertical shrink by 1/2, left 4. So I'm going to move it left 4. So here's my new origin. So draw in your vertical asymptote. Vertical shrink. Okay, remember that first point, that 1, 0, doesn't get affected by anything vertical. It's still right 1, 0. The next point becomes 10. Instead of 1, it's going to be 1/2. So it's going to go over 10. But only go up half. So it's going to barely get above that x-axis, but it's there. Lastly, let's look at 10. Now, it's going to go down 2, so go down 2, change your origin, put in your vertical asymptote. Now I want you to be really careful. Look at this. This is base of 6, not 10. Everything we've done so far has been base 10. That means our points are changing a little bit. It's going to go 1, 0. That one will never change. But instead of 10, 1, it's now 6, 1. Okay? So from my origin, I'm going to go right 1, up none. Then I'm going to go right 6 and up 1. All right? So then my logarithm looks like that. So be aware of the bases. Okay? If it doesn't have anything there, that's the understood 10. Okay? But if it does, if it changes, you gotta adapt your points accordingly. All right, let's try the backside. Okay, on the backside, there's just a couple more things I want to mention to you. The domain of the log function will only be restricted by the left and right shifts of the equation. Okay, and why is that possible? Because it moves the vertical asymptote. Okay, it moves that vertical asymptote, and that determines our domain. The range, if you remember, the range is always just negative infinity to positive infinity of logarithms, okay? So really what we're concerned about on this page is the domain. So look at the instructions. It says define the domain, or determine the domain of the function without graphing it. Don't use graph it. But it says to use both set and interval notation. So we got to work on these notations, making sure we get them. Look at number 11. So you look at your equation, you look at the log, okay, it's base 10, and then I ask myself, is it moving left and right at all? Well, if it's not moving left and right, then it's going to just be the same as our parent function. So look back at our parent function. What was the domain there? Well, it went from 0 and greater, but it didn't equal 0, it just approaches it, right? So we say greater than 0. And then in interval notation, we write that as parentheses 0 to positive infinity. Look at number 12. Base 2, don't let that mess with you. Look at this minus 10. Is that moving left or right or up, down? Hopefully, since you recognize it's not in parentheses, you realize that this is just moving it up, down. It's not messing with the left and right shift at all. So our domain hasn't changed. It's going to be x is greater than 0, because it's not going to cross that asymptote, but it will approach it. And in interval notation, it'll be 0 to positive infinity. Now look at 13. All right, there is a vertical shrink. That doesn't matter right now. We're just talking domain. This means it's going opposite logic, right? So this asymptote is moving left 10. So that means that my domain is now, x will be greater than negative 10. All right, it's still going in the same direction. It's just shifting this thing over to the left 10 units. Interval notation, that's just a parenthesis with negative 10 to positive infinity. Look at 14. There's a lot going on 14, but the only thing that we really are concerned with is the left and right shifting, this part right here. So think about what that's doing. Well, that's moving it left 7. So my domain will be, x will be greater than negative 7. So make sure you change your sign. And in interval notation, that would be negative 7 to positive infinity. It might help you to like sketch a little graph on the side to kind of visualize what's going on. So don't be afraid to do that. That's perfectly fine. You do have to stop and think. You're not going to be using your calculator to do this part. All right. Now, let's look at the bottom here. Here we're going to be writing the logarithmic function matching each description. So pay attention to the parent. Look at the base on that. Make sure we put log base 2 wherever we do it. Let's look at the description though. It's shrunk vertically by a factor of 1/5. So where's that going to go? That's going to go in the very front. Translated up 2 units, so it's going to be a plus 2 in the back. And reflected over the x-axis, that means a negative in the front. Okay? So let's do that. We'll say f of x equals, put our negative out. What else goes in the front? The 1/5. Now we put the base, log base 2 of x, and then we put plus 2 on the back. Let's look at part B. The parent function is a common log of x, so remember it's base 10, stretched vertically by a factor of 7, so that's going to go in the front, and then 4 units left, so that's going to be x minus 4. I need to put that in parentheses, okay? So then f of x equals, so it's going to be 7 log base 10, and now my x has to be in parentheses because I need to put that, oops, not 7, it's 4. X minus 4. Okay, so hopefully all this makes sense to you and you'll get the hang of it, and we'll see you in class.